So, hi Annie.
Hi Janakiraman.
So, let's continue with our discussion on filters,
Yes.
right? So, if you remember, we started this whole discussion on, addition, superposition and all that. We started with a sound mixer, right?
Yes.
And
That's right.
so, why don't we just go back to that and revisit some of these, knobs that are there, Ultimately, we wanted to sort of understand what a sound mixer does by the end of this series of lectures, right? So, each of these columns represents a channel, okay, and effectively it's like one microphone output or one keyboard output or whatever, right? It's coming in there, and there is this aux 1, 2, 3 and all that stuff, right? And of course, you see the slider here on each
Yes.
on each of these channels. It's basically going to control some resistor inside that will control the amplification factor,
Yes.
right? And we know how this
That's
part of the circuit works, right? However, if you look at the top part of this mixer, right, there are these green knobs
Yes.
which you can rotate clockwise or anti-clockwise,
That's right.
and you see there's something called high in
Yes.
it. Okay, maybe let me try to amplify this a little further. Yes, right?
Yes.
So I think, does that make it look better?
Yes.
Yes, good. I think this is absolutely
Okay.
right.
I see high, mid, low.
Low,
Yes.
right? And what is it? It gives you some numbers also, some 10 kilohertz. The low says
That's right.
100 hertz,
That's right.
right? So,
Yes.
so what's your guess? What do you think this would translate to inside a mixer?
I think it's connected with what we have been learning so far in the last few classes.
Right.
Most likely it refers to the frequencies
Exactly, the frequencies and the filters.
and the
right?
filters.
So, if you're talking about 10 kilohertz, we're talking about amplifying. Now, we are not talking about amplifying the entire signal, but only frequencies above a certain threshold or below a certain threshold. So, the low corresponds to some sort of low pass filter, right? Your amplifying frequencies may be around and below 100 hertz, right?
Right.
10 kilohertz, it says high, is probably some high pass filter around and above 10 kilohertz, right? Now, there is something in between which is very interesting. It's called mid.
Mid.
Okay, and that corresponds to some frequency range in between.
Yes.
Okay, so let's maybe go back, and maybe we should also start plotting certain amplitudes as a function of frequency.
Yes.
Right, we are used to plotting it as a function of time. So, just to remind the students, this was effectively our V in of t, RC. This was the low pass filter, right? And
Yes.
then you had the high pass filter, which you redrew very nicely last class. Okay, effectively it's just looking at the resistor voltage of the low pass filter.
That's right.
Okay, V in of t. I'll call this R1, C1, R2 and C2.
No, the other way. C2 and R2.
Sorry. C2 and R2, exactly. Okay, and the output voltage is always here. V out of t, V out of t. This is the high pass filter, okay, and
Maybe we'll call this V out 1 of t and V out 2 of t.
yes, absolutely. So, this Vc of V out 1 of t, okay, was, if you remember the amplitude,
Yes.
I'll just write it as the magnitude. Forget the sinusoid part.
Yes.
Okay, I'm going to write it like this: 1 plus omega naught squared R squared R1 squared C1 squared.
Yes.
Okay, and the high pass filter is input amplitude minus it's a slightly more complicated form, but let's just focus on this
Yes.
expression. Okay, so what I want to now plot is the x-axis is going to be
Omega naught.
omega naught. Okay, and this will be in radians per second.
Yes.
Okay, and my output and my y-axis is amplitude of V1 of t. Okay, So if you remember the discussion we had, we said that when omega naught R1 C1 was much less than 1, effectively this would just be close to A.
That's right. That's right.
And it would start falling off after somewhere at 1 by RC. It would go to 1 by root 2.
That's right.
This is what we saw.
That's right.
So it would be something like this, right? This is amplitude A.
Yes.
Then we have to look at A by root 2, which is about 0.7. Yeah. So somewhere here,
Yes.
right? So 0.707 A,
Yes.
right? Which is A by root 2. So this, and on the x-axis, I'm also going to look at the point which corresponds to
1 over
omega
RC.
naught equal to 1 by RC.
Yes.
Okay, at that point, the amplitude has to fall to 1 over root 2.
1 over root 2.
Right? And
Yes.
I mean, all these are nice continuous functions.
Yes.
So they'll gradually fall off
Correct.
like this.
Yes.
Right? This is
Yes.
effectively what a low pass filter's frequency response looks like.
That's right.
That's the term that we use in electrical engineering.
That's right.
It's called frequency response.
Yes. In fact, if I were to imagine when omega naught is much larger than 1 over RC, the expression for amplitude, the omega naught RC portion becomes much larger than 1. It seems to go as 1 over omega naught.
Yes.
Right?
Exactly.
So it should be asymptotically going to hitting the x-axis.
Yeah.
Getting closer
exactly,
and closer.
Right?
Right?
So exactly. So let's also look at that. So you're saying that mod of V out of T is approximately equal to A by
Omega naught RC.
right?
Right?
So
when
it's
omega
like
naught is much, much larger than 1 over RC.
Yeah. So this is like a 1 over X.
That's right. So this same curve, if you extend it, it will slowly go,
It'll basically go like this, is what you're saying?
Yes, it will go as 1 over omega naught as it asymptotic.
And asymptotically gets to
That's right.
0, right?
That's right.
Exactly. So this is the characteristic of a low pass filter, right? And our students are going to see this in various courses multiple times, and you will learn how to solve such things in different ways, right?
Absolutely.
That is electrical engineering, right? In some sense. Now, how do you think, if we were to plot the frequency response of a high pass filter, what do you think that is going to look like?
So,
Right? So let's look at HPF, okay, and we are going to look at VO2 of T, which is across the
yes.
resistor.
Yes.
Yeah. Okay.
Absolutely.
So, this is mod of VO2 of T. Okay. Mod as a function of omega naught.
Yes. So I'm going to go back to the same old trick we did when we did the analysis.
Yes.
So we saw that the high pass filter looked like the input minus the low pass filter.
Yeah.
So if I were to take the previous plot
okay,
and just plot the input,
yeah,
that would just be a constant magnitude.
Exactly.
Right?
Right.
And I can just subtract my low pass filter frequency response from that flat line.
So you're saying that the amplitude here,
yes, my
like
input
this?
frequency response
yeah,
will look like that, because what I'm putting in A sin omega naught t for all omega naught.
right,
Right? So what I would do, this is my input.
Yeah.
I would just subtract the low pass VC of t. I would get the high pass filter response.
Right. So if you do that at very low frequencies,
Yes.
you subtract A is just A minus A. It has to start with 0.
0. That's right. That's
and
right.
then it has to sort of gradually, I mean, even this one, the black line I've drawn is not a straight line. It's asymptotically.
It's asymptotic,
getting, right?
That's right.
So effectively, it would.
I will get something that is very small for low frequencies.
Yeah.
Very close to
A
for high frequencies.
Exactly. So I will do the same thing here. This is my A, and again, as all this is asymptotic.
Yes.
So I mean, no, maybe I should draw it in a different color. This is my V out.
Yes.
Right? Something like this.
Perfect.
And you will have, at the 0.707,
Yes.
you will have another sort of, that's a salient point on this.
That's right. And that will, that might happen, I'm guessing, somewhere related to R2 and C2.
R2 and C2, right? So maybe this is it just 1 by R2 C2?
I suspect so.
Right?
Yes.
Okay, good. So we will verify this
Yes.
in an assignment. We will not do it.
We'll
right?
not do it now. Yeah.
Okay, great. So now I want to see how do we construct that mid filter, right? So first let's look at how the frequency response of a mid controlling knob should be, right? What do we want? So the low pass filter, effectively if you look at that mixer, it set something up to 100 hertz. So this RC will correspond to somewhere, correspond to, I'll just put an arrow, so
Yes.
correspond to 100 hertz.
Yes. So we'll just call it R1C1.
Something, R1C1.
That's right. So that is 100 hertz.
Something we wanted, right?
That's right.
Or 1 by 2 pi times that, doesn't
Yes.
matter, something, right? And then we said there's another thing which was like 10 kilohertz, right?
Yes.
So something, this will correspond to some 10 kilohertz.
Yes. So most likely some 1 by 2 pi R2C2 or something like that will be 10 kilohertz.
10 kilohertz, right?
Yes.
Yeah. Now, this mid frequency it's neither too high nor too low. So
That's right.
maybe we want to amplify frequencies from 1 kilohertz to maybe 6 kilohertz or something like that. Okay. So what is the frequency response first of all? Okay, this is, we'll give it a name later.
Yeah.
Okay, we'll not worry about the name. This is VO3 of t, by the way. I'm going to call
Yes.
it. Okay, this is a black box. We have to build this circuit now. Okay, V in of t, which is the sinusoid of frequency omega naught.
Yes.
We're going to get VO3 of t now.
Yes.
Okay, I don't know what the circuit is, but the behavior has to be something like this. Low frequencies you cut out,
Yes.
you go up,
Correct.
keep it flat, then drop.
Makes sense.
Right?
Yes.
Absolutely. So this is what you want, and it's evident here from now that the point at which this graph goes to 0.707.
I'll have 2 points.
Exactly. Right? This is A. This is A by root 2.
Yes.
Right? There are 2 points when this
Yes.
curve goes to that value.
Yes.
So there's going to be some omega L and omega high.
Yes.
Okay, this is going to correspond to some R2 C2. And this is going to correspond to some R1 C1.
Yes.
So how do we build this now? What do we do?
I'm noticing something interesting.
Yes.
The lower part of it looks like the high pass filter's lower half.
Yeah.
The upper part of it looks like the upper half of a low pass filter.
Yes.
Maybe if we combine the two, we might
Okay.
have a chance.
So what do we do? What do you think we should do? Should we? What can we do? Suppose, what are the possibilities? Are you suggesting we just add them?
Well, if we just add them,
Yeah.
that may not give us what we want.
Okay.
Because at lower points, the high pass filter actually gives you nothing,
Yeah.
but the low pass filter gives you the full input. If you add the two, you'll pretty much get the low pass filter's value.
Exactly.
So adding the two may not be the right thing.
Right.
So maybe multiplication?
Exactly. Right. You need to, in some sense, take this frequency response and multiply it.
Yes.
Where either one happen to be low, you want it to be low, but
Yes.
when both are high, you want it to be high, right?
Yes.
So that is a great idea, and if I had two switches, if I wanted to do an AND operation, I would just put them in series,
Yes.
S1 and S2. Only when S1 and S2 are on, you get a thing. So the idea is to do the same thing in the analog domain, cascade them. Take the
That's right.
output of one and then feed it to the other, right? So what we are going to do is do this. V in of t, R1, C1. This is, maybe I can remove the switch, R2 and C2.
Okay. So now you are looking at, so
Oh, sorry.
we want to cascade a low pass
Exactly.
filter with a high pass filter.
So therefore I got to put a capacitor here
Yes.
and
So I understand. You are taking the output of the low pass filter and giving it to the input of the high pass filter.
Exactly.
Right?
Exactly.
So you basically, it's almost like taking two separate filters and cascading them,
And then
which is what you
cascading
said.
them. Exactly. Right. So I am going to look at VO3 of T across this resistor.
Yeah.
Right. Now, how do we design these values? Okay, we should be very careful in picking these values, because
Yes.
if we don't, we could get something very funny, which basically does nothing useful for us. Okay,
Yes.
so we'll look at that.
Yeah.
So we know that the R2 C2 is going to correspond to the lower threshold,
Yes.
omega L. R1 C1 is going to correspond to the higher threshold.
Yes.
Okay, so effectively, and like you said, the first half looks like that, some response of a high pass filter. Second half looks like that of a low pass filter, right? So the cutoff frequency of the high pass filter must be lower than the cutoff frequency of the low pass filter,
Yes.
right?
That
So
makes sense.
Exactly. So here, sorry, let's just, right, this is the cutoff frequency of the low, this is the,
Cutoff frequency of the high pass filter.
yeah,
Omega
but this
L.
is the high pass filter's
Cutoff.
cutoff,
That's right.
okay, and this is the low pass filter's cutoff.
Yes.
Okay, so we have to be very careful that omega L is less than omega H.
Yes.
If we did the opposite, what would we get?
I would guess that you would get nothing,
You would get
because you are
nothing.
multiplying most likely 0 with 0 in all the cases.
Exactly, right? So if you look at the case where the low pass filter's cutoff was lower than the high pass filter's cutoff, it would be something like this,
Yes.
right? And then the high pass filter would start like this here.
Yes.
Maybe it would go all the way here,
Yes.
and then go like this.
Yes, if you multiply
these two, and you will get effectively
Some small value all
almost
over the
zero
place.
across all frequencies. This you can call a no pass filter.
Yes.
It passes nothing through it. Okay.
Yes.
So therefore, this is useless and cannot. And you should be very careful to pick the R's and C's appropriately. Okay. So now, if we pick these R's and C's in this manner, then what you get is, in a certain band you allow frequencies to go through, and you cut the frequencies outside this band.
Yes.
So a good name would be band pass filter.
Yes.
Okay. So now let's get down and look at an experiment, right? So let's look at this experiment. I want to choose R1 as 1.2 kilo ohms, C1 as 10 nanofarads.
Okay.
Okay. C2 is also, maybe I'll put that in a different color. C2 is also 10 nanofarads. R2 is 100 kilo ohms.
Is there some magic to choosing these numbers? I think we should look at that at the end once we finish the experiment.
Yes, exactly. Okay, so let's look at that, but also let's evaluate these values first and keep
Yes.
it, right? R1 into C1 is equal to 1.2 nanofarads into 100. Sorry,
1.2 kilo ohms
kilo ohms
into 10 nanofarads.
into 10 nanofarads.
Yes. So that seems to be about 12 microseconds.
Yeah, or again, let's make this 1K,
1K, sure.
right? So it is
That's about 10 microseconds.
10 microseconds.
Yes.
Okay, so
So that's about 100 kilohertz?
no, we have
No?
to be, no, that's about 100 kilo radians per second.
Kilo radians per second.
Yeah, so this
That's right.
corresponds to 100,
Kilo radians per second.
yes,
Right?
kilo radians per second.
Yes.
Okay, but that corresponds to what? 100 by pi.
100 by 2 pi.
100 by
Yes.
2 pi, 100 by 6.
So that's maybe about 14, 15 kilohertz?
14 or 15 kilohertz.
Yes.
Right?
That's
Okay.
right.
So 100 kilohertz, and I'll just put that here. The cutoff frequencies for the high pass filter is what, about 14 kilohertz?
Yes.
Some approximate number.
approximately.
Yeah. Now, no, what is this? I was looking at the, sorry, this is the low pass.
This is the low pass, correct.
This is
oh,
the-
I see. It should be on the next this thing.
Yes, exactly.
Yes, the low pass cutoff is
Yes, exactly.
14 kilohertz or
Yes,
16 kilohertz,
exactly.
I think.
So that I'll just write it in black here.
Yes.
Sorry. So this is 1 kilo ohm into 10 nanofarads. Okay, this is equal to 100. This corresponds to 100 kilo radians per second,
Yes.
which corresponds to 14 kilohertz.
Yes.
Okay, and the top one we need to reevaluate.
Yes.
Okay, great. So what is the top one? It's basically for the high pass filter. Okay, and what is this? We are talking of 100 kilo ohms.
Yes. So the resistance is 100 times, the capacitance is the same.
Yeah.
So my guess would be 14 by 100.
Exactly, right? So this will correspond to,
So that's about 140 hertz.
yeah, this is about 1 kilo radians per second, and this would be
Maybe 140 hertz or 150 hertz,
hertz.
something like that. Yeah.
yes. Okay, so effectively we are looking at a frequency response which looks something like this. Okay, if I plot it with respect to the frequency now, I am not plotting with respect to omega naught, I am plotting VO3 of t. Okay, amplitude at 140 hertz, you have a cutoff here. Okay, and then you have something at 14 kilohertz.
Yes.
So this will start like this, maybe, yeah, something like this.
Correct? Yeah, I think so. Yes.
Okay, some picture like this is what we should expect. So, you know, as you go below 140 hertz, it'll start diminishing. Above 14 kilohertz again, it'll start diminishing. And in between, you should see it go up and then saturate for some time.
That's right.
Right?